Thanks, everyone, for joining. My name is Ruben Amarasingham from Pieces Technologies. I'm the president and CEO. And so very excited to meet you all. And I've been working, and my team have been working in this space of clinical outcomes, predictive modeling, and decision sciences for almost 10 years now. And we're excited to talk to you about some of the advances that we're working on at Pieces Technologies that uses artificial intelligence to help health systems. So let's start off. Just starting off, just right off the bat with a classic artificial intelligence task. This is our work that our machine vision group has been doing at Pieces Technologies. This is what I would call a classical artificial intelligence task, which is machine vision or image recognition. In this particular case, the Pieces system is using a deep neural network to separate and identify a benign skin lesion from a malignant skin lesion, in this case melanoma versus benign keratosis. We're very excited about this work. There's a lot of opportunities in using artificial intelligence and deep neural networks for image classification in medicine with cardiovascular imaging, wound care, and malignant evaluation of dermatologic conditions. But I would say that image recognition is actually a very straightforward artificial intelligence task, one that we think has significant applications. But it's straightforward because you're dealing with billions of points of data, and you're able to use neural networks in a way where it excels. The problem with a lot of aspects of medicine is we know that the decision tasks in medicine are not as straightforward as straightforward machine vision tasks. And so we want to walk you through what we think is a classic example of that. And if we can do it, is related to our mission statement, which is how do you advance health in highly complicated health systems with incomplete data, ambiguity, uncertainty. And so as a decision sciences company, we're interested in all aspects of those kinds of decisions. And you have to think about artificial intelligence and apply it to the problems where it really makes sense. Our particular view of artificial intelligence is to use what we call human assistance, human-assisted AI, or human-in-the-loop artificial intelligence to solve some of these problems. So how do we do this? Our core platform is called Pieces Decision Sciences. It's cloud-based, and it's patented, and it uses a significant amount of natural language processing and machine learning to achieve some of these tasks. One of the core elements is that the platform interacts with our clinicians to continually learn and improve. And that allows us to overcome some of the messiness and uncertainty that you sometimes see in healthcare. So the Pieces system essentially is designed to follow a patient care journey. So every patient has what we think is a timeline. That timeline could be 365 days. It could be just 3 hours if it's an elective surgery. It could be 5 years if it's a cancer outcome. And so Pieces essentially follows a patient throughout this time course and tries to optimize every decision that's occurring through this process. And so if you imagine how Pieces does that, we look at 5 critical steps. Identification, what's actually occurring with the patient. Then prediction, which is what may occur and when will it occur. And a key step for us as clinicians that are operating this technology is how do you notify the right person, or activation? And we believe in EMR workflow activation, so we're fully integrated with the electronic medical records. Then monitoring, are we on path? And finally, one of the most critical steps is, given where outcomes can go wrong, how systems are configured differently, how do you learn and how do you assist the learning process? And that's where we apply the human-assisted artificial intelligence. Pieces takes all the information from both electronic medical records and non-EMR sources and combines this information. So let's walk through how this might work for one of our problems. Sorry for the blank there. So this is our current sort of use cases that we're applying these 5 steps towards. We applied this inventory sort of growing every month. And essentially we're saying for all clinical outcomes and operational outcomes that matter, we believe you have to apply those 5 steps and monitor, have those algorithms monitoring those 5 steps all along the way. We want to tackle today a problem that health systems are really challenged with. How do you reduce length of stay? How do you optimize the patient trajectory? So in this particular case, we think there's 5 critical questions to ask that traditionally have been difficult to answer. These questions are who can be discharged today? When can they be discharged? What actually needs to be done for the patient? And how can I help as a health system without getting in the way? These questions, who, when, what, why, and how, are actually the same questions that we ask medical students to master when they're coming up with a differential diagnosis. So what we're starting to see is these cognitive technologies that are trying to approximate the way a clinician might approach a problem. The question is, can you do this for all 1,000 of your patients simultaneously in real time every hour in the hospitalization? And this is what Pieces essentially does for this model. So the first step is those first 3 models. We'll walk through identification, prediction, and activation. So this is what we call our Pieces Command Center view. This is a view of every single patient in the hospital. It's changing constantly every day, and it's a live view of where they are in their hospitalization. Let's break this down for a second. So to accomplish those 5 questions, you need several algorithms running in the background that are interacting with each other. If you look at on the y-axis, for each patient, you have, a predicted probability of discharge. And so if you're at 100%, that would mean that your probability of discharge is very high. And that means for that person, they can leave today, 100% chance. 0%, 0 probability on the y-axis means obviously they're not going to be able to leave that day. We then displace that against the the x-axis explains the length of stay. Pieces is predicting when can this patient go home. So on a 0 day would mean that the expected length of stay is today. If you looked at all of these patients with lupus erythematosus and compared this one patient with lupus erythematosus, you would imagine that if today is your day of discharge, that's your 0 day. Post-0 is patients that they're past their prior expected length of stay. So you're immediately looking at all the patients that are remaining after their expected discharge. The key element is, where do you focus? So all the patients that Pieces has identified as high probability of being discharged today and are prior to their expected discharge, those are high value targets for discharge. So Pieces is taking every single patient, it's reviewing all the doctor's notes, the nurse's notes, the case management notes. It's understanding what they feel is left to do for the patient and identifying where they need to fit. If you're an individual in the upper left quadrant, you don't have that many more steps to be discharged. And if you're discharging them ahead of stay, the hospital's obviously making a profit in that circumstance. But that's not enough. This is enough to say who needs to be discharged and when. But the question then becomes, what do we need to do for this patient? So Pieces, here you're looking at a view where all of the colors that are represented for each dot represent different reasons why they need to be discharged. So some of these reasons include that there needs to be a family discussion. So Pieces identified that this is a person with end-of-life care and they have a need to meet with a chaplain. Another case may be symptom resolution. So Pieces has reviewed the note. It might have identified this person in the upper left quadrant that they have a diagnostic test that's pending. And then it would indicate that a clinician needs to be notified, and it will notify the clinician. So it's identified who needs to be discharged today, what's the likelihood of discharge, are they ahead of schedule, what's remaining, and then it would notify the appropriate care team member. It could identify that someone needs to go to a nursing home to receive their follow-up care, and it would notify case management. You could even imagine that this individual has a symptom resolution problem, you need to notify a nurse. Someone in the bottom right quadrant, there's complex discussions around end of life, and you'll need to notify the chaplain. So essentially what you're seeing here is we've now identified when, we've identified who, we've also identified what needs to be done. This is essentially Pieces reading the note and understanding that information. How does it do this? Pieces is integrated with the electronic medical record, so it'll notify directly in the EMR this information. This is what a physician might see. And just to show you, it may be hard to read, but essentially Pieces has read the note and it's going to tell a physician, we're currently awaiting for further recommendations from hematology oncology as to whether the patient will receive inpatient versus outpatient chemotherapy. So it reviewed the note, it identified that's the piece of information that the physician needs to know and sends it to the physician. For a nurse, this is an off EMR view, but just for example, this could be a nursing list. And here's a patient that came in with the malignant neoplasm of the anus. And so it's a surgical procedure that would need to be done. And Pieces read the note and said, for this patient to go home, a symptom needs to be resolved. And specifically, it's identified that the surgeon wrote that discharge is pending return of bowel function, ROBF, which is a critical piece of information for a nurse, because then they can record bowel movements, make sure they're aware of that, so to allow for the discharge. So you're getting highly choreographed care based on what Pieces is identifying. So we've now said identification, prediction, and activation. All of those steps could be applied for much more than just throughput management, for really the entire clinical inventory. But those are those three key steps. The next step is monitoring. Are we on path? So we've activated the right individuals. Are we following through? So the monitoring is really critical because this is the patient trajectory that you're trying to optimize. In the case of a relos case, which is an ideal length of stay, here might be an ideal patient trajectory. A person comes in, they're ahead of schedule as far as their length of stay, and they're moving nicely up to an ideal patient trajectory. But we know that in actual clinical care, it's much more messy than that. We thought a patient would be discharged, something happened and they weren't discharged. And so a critical element for Pieces is it follows each patient hour by hour and note by note to try to understand what's occurred in the hospitalization that needs to be modified. So let's look through how that might look. Here's 3 patient journeys. And imagine a case where patients coming in and it's now they're at their expected length of stay. So they're still not at their high probability of discharge. They move forward and now Pieces is saying very high likelihood of discharge. And it's particularly noted that discharge is likely tomorrow after a left heart catheterization. Suddenly, their probability drops. And what's happened is the physicians noted that there's a new bacteremia. It's unclear what's causing that bacteremia. And now we have to own a transesophageal, we have to order a TE or transesophageal echocardiogram. So now we know the hospital knows that there's been a new etiology that we're not aware of, and an echo needs to be ordered, and that awareness is now present, and the probability of discharge has gone down. It then follows through and is watching each step to see those things are occurring and notifying the right individuals. So a TE is ordered, and then we're ready for discharge. All of these insights, Pieces following and tracking, and we call that decision assets. Each of these are a new form of data currency, which is what was the decision at any point in time. We're recording that, and Pieces is learning from every decision for the next decision, the next patient that looks like that. So that's monitoring. And now we're moving to the critical step, which is how do we take all this information from the patient journey and learn from it at every point. In this step, we think that an unsupervised artificial intelligence system is not adequate. It's adequate for problems like image recognition. It's not adequate for the types of messy problems that we've described. And so we use a human-assisted AI system. So in this particular case, we use it in 2 ways. Pieces identifies situations of ambiguity. And in workflow, we'll trigger our own clinicians that are working on the system for feedback. And that can occur with all of our health system clients. And it gets faster and faster, which allows for the scale. It also does it after the fact. So we can review a health system's progress when there's an adverse event account and actually do chart reviews on these patients very quickly. So how might this work? Imagine a patient trajectory where the course did not go as planned. The patient went through, and on the last day, instead of seeing the nice slope upwards that you would expect for a discharge, it's at 40% probability, so something went wrong. PIECES then reviews the entire case. It goes backwards and reviews all the notes. It assesses what occurred. It's indexing all the notes using natural language processing. And in these cases, it feels very confident about these issues. In one particular situation, it said if U/S negative, is this a valid term that we should be bringing into the discharge prediction? In this particular case, it's presented back to our clinicians who are reviewing it and indicating actually this is if ultrasound is negative, a discharge can occur. So that was clearly a discharge placement, a discharge decision, and it takes that information. So how does this work? Here's actually a live rendition of our system working. So it's presenting this information to our clinicians. It's happening for all of the decisions that are occurring across thousands of patients across all of our health systems. And each decision reinforces the next decision. And our physicians' review time for each particular problem gets smaller and smaller. And this is where we're calling curating these decision assets that are then applied to the next decision. This is our human-assisted artificial intelligence system, and we apply this across all of our conditions. One of the things that's been very exciting about this process is that we can apply this system for a lot of conditions outside of just the condition of reducing throughput or other specific adverse events. And we've been able to apply this to the human review that health systems often have to do. They employ a lot of labor doing chart reviews necessary for core measures, necessary for regulatory burdens, and chart reviews that normally take 90 minutes to 4 hours by a trained nurse can be done by PIECES in 7 to 10 minutes with human assistance. And so we're able to reduce the workforce required for some of these chart reviews using this system. What finally occurs is that you can see that the trajectory and the modeling changes as a result of all of these reviews, and the probabilities around the trajectories change and are there configured to that health system. Let me end where we started, which is what I just described to you is one clinical and operational use case, which is using natural language processing, human-assisted artificial intelligence to optimize and choreograph the clinical journey of a patient to optimize their care stay. We apply all 5 of those algorithm engines to the entire set of clinical and operational use cases. We have about 80 right now, and it continues to grow, which includes the chart review process that we described in the end. So we're very excited about this platform. We're excited about you all coming in. We think that there's a number of ways to use it, and we'd be happy to talk to you about this process at our booth, which is 7785. Thanks for this amazing turnout. Really appreciate you coming by. How much time do we have now? We have about 5 minutes, so if there's any questions from the audience, we can take them. Yeah.
How do you avoid redundancy between the alerts that you generate and the communication already being done between the care team members?
Yeah, so one of the ways that we do that is the question was, how do we make sure we avoid redundancies between what's already occurred and what hasn't occurred? So the key element there is that PIECES is monitoring to see whether appropriate steps were taken that already indicates that the action has been taken. And we can use natural language processing or review of the order sets. Yes, because it can read the notes. Yeah. Thanks.
Yeah, hey, I work for Persistent Systems. My question is related to the, you mentioned about the algorithms that you have built as a part of this system. NLP, are you using public libraries or are you using some custom libraries that you created for NLP?
The NLP platform that we built is completely proprietary, so we built it on our own. Yeah, we use existing ontologies that have existed out there, but the platforms ourselves. Thank you.
You talked about supplementing nursing chart review as well. Is that in a clinical setting or more on the administrative side? And what does that process look like?
It can be both on the clinical and the administrative. So typically those chart reviews involve core measures or other things that are administrative. But we can, as we mentioned, we can apply it in the real-time task as well. Thanks. All right, thanks.